Hello and welcome to this third video on compiler design. So last time we talked about lexing and parsing, and this time we're going to look at name binding, what it is, why we need it, and how to implement it. In the last videos, like I said, we talked about lexing, parsing, and we now have a compiler that can look at a source file and produce an abstract syntax tree out of it, an AST. And that is the data structure we work with from now on inside the compiler. And name binding is about connecting identifiers to the places where they're used. So whenever you declare something, then you need to make the connection between where the place where the thing is declared and the place where the thing is used. So here we have to first talk about why we need this, and perhaps it's not exactly obvious, but if you have an identifier like this, in this expression or in this function declaration here, you have a function taking an integer parameter called I, and then the body of that function is just returning I. Now if you look at this function, you notice that I is declared here and used here. And if you want to do something as simple as just doing type checking, you need to know that, well, I is of type i32. It's an integer declared as i32. And so you need to connect this use here that is in the body to the declaration side here, which is in the parameter list. So it's, for type checking, important, but it's also important whenever you need to generate code, because you need to know where this thing was located, what is the type of this thing, and so on and so forth. So every part of the compiler will need to know about this information. And that's why we need to do that, essentially. Now, scoping rules, so when we connect identifiers to the place where they're declared, this follows a certain set of rules that what I'm going to call scoping rules. If you program in C, you already know a lot about scoping rules. There's already essentially the notion of a block, and within the block, this is often called in C terminology also a scope. So within the scope, you can say, well, I have a variable I, and this variable I is only visible within the block. I cannot use I here, for instance. This wouldn't be allowed because this is outside of the block, right? So this is a scoping rule that everyone's familiar with. You can also, of course, shadow. So there's another scoping rule. You can shadow I by redeclaring it, but you cannot redeclare it in the same scope. That is not allowed. What you are allowed to do, though, is declare it a second time, but within a scope nested in the original scope. So whenever I see a use of I, let's say here, I need to first look at the current scope, figure out whether I exists. In this case, it does, and use that. And if it does not exist, because maybe this one is a K, for instance, then I need to look at the parent scope and figure out whether I exist, and so on and so forth. So I essentially have this notion of a scope, and it's not just one scope, it's a stack of scopes actually. And whenever I need to look up an identifier, I need to walk this stack of scopes. All right, that's for scoping rules. At this point in Foo, the scoping rules are a bit similar, right? I mean, in terms of blocks, we also have blocks, we also have functions, and we also have the notion of scoping and shadowing and things like that. However, there's a large difference compared to C. In C, you know, when you declare a function, f, and maybe I'm giving this a body, then it's available later on. So if I say G, F, that's valid C code, right? I mean, G calls F, and F is available the moment you declare G. Now, if I were to do this, though, basically move the body of G, with the declaration of G, up before F, that would not be legal C code because F is not declared at this point. The compiler will complain. However, in Foo, that is not the case. In Foo, you're allowed to do this. So in Foo, you can do something like fun F I32 is equal to I. And then let's say you can do fun G I32 is equal to F of I. That's perfectly allowed, perfectly fine. So the rules are a bit different, and in that sense, it's implemented slightly differently. There's a pre-pass, so at the top level or within the block, because you can also declare functions within the block. At the top level or within the block, we're also going to have to first do a first pass where we record the functions that we see, or the structures for that matter, because it also applies to structures or enums, and also types, by the way. So whenever we see an alias, a structure, or an enumeration, or a function, we write it in the current scope. We say, well, this is available in the current scope, and then we go over all the content of the scope. So maybe there's something in the scope like a while loop or whatever, some form of code, maybe that does a print of f or print of g of 33 or something like that. And we only go to actual contents of the block, the actual statements that are not declarations, only if we have already added all these declarations to the environment. All right. So that's valid, of course, for blocks, but also valid for the top level. So at the top level, we also do this very same thing. We first place declarations in the environment, and then we type check every declaration on its own. All right. So that's for the scoping rules and the order of declaration. Now, the implementation of this, as you can imagine, uses a stack. Because we have a stack of scopes, there's a lot of sense to implement this with a stack because it's essentially very natural. And in terms of code, in terms of C code, though, I've implemented this with a list. The stack is represented as a list because it's simpler to implement, because I don't have to care about growing an array or reallocating the elements because I need more space. I just have a list and I'm allocating elements of that list. Each element of the list is a scope that contains a hash table, that is the list of symbols declared within the scope, and the AST node which created the scope. Maybe it's a while loop, maybe it's a block, maybe it's a function expression, maybe it's a function declaration, maybe it's something like that. And we need to keep track of what created the scope. And then there's, of course, the back pointers to the other elements of the list. So the back and the next pointer, because it's a doubly linked list. So if we look at the code, first of all, let's look at the header file. The header file looks like this. There's a notion of an environment. It's just a list of scopes. As you can see here, we maintain both the beginning and the current scope being the top of the stack, so the scope we're currently within, or scope we're currently looking at. And there's the log, which is helpful if I want to report an error that an identifier was not visible or hasn't been declared. And we have functions to create that environment, and then we have functions to bind the AST or bind the identifiers that appear within an AST node. So first of all, what does it really mean to bind the identifiers that appear within the AST node? Well, if you recall, we have this the AST type here, and we have paths. Okay, a path is either just an identifier like A, or an identifier with a type if you instantiate it, followed optionally, it's not necessarily the case, by other identifiers like that. So it could be B, I64, .c or something like that. We have essentially a sequence of things with optional type arguments, and that's what a path is. But you may also have a path which is just one identifier, and if it's one identifier, then you only have one element, and the element has only one, has no type arguments, and it has to be mapped to the place where it is declared, which is why we have this target field, which represents essentially what it is pointing to. Maybe I'm going to call this decl site because it's clearer what it means, right? It's the declaration site of the element. Now, if you go to the name binder itself, this is the header file that we talked about. If you look at the name binder itself, the implementation of these things, you have the notion of a symbol, which is just a pair, a name with the place where it is declared. And you have then the notion of a scope, which is a hash table containing all the symbols that are declared within the scope. The AST node that created the scope, the while loop, the function, the block, whatever that thing is, and pointers to the previous and next scopes. A function to compare symbols for the hash table, obviously. We have functions to create a scope, function to create the environment and free the environment, as mentioned before. And more interestingly, we have functions to insert a symbol within a scope, or within the environment rather, which essentially just inserts or tries to insert a symbol within the current scope with just this function that inserts the symbol within the hash table of the current scope. And if that fails, it means that the symbol already existed, which means we emit an error message saying, hey, you're trying to redefine a symbol here, you're doing something wrong. Then we have a function to find the symbol, and this time it's a little bit more involved because finding a symbol, like I said, is just not looking at the current scope, but you also need to look at the parent scope. If you couldn't find the answer to, or the actual identifier you're looking for in the current scope, you need to look at the parent scopes. So what you do is you start with the current scope, you look at the list of symbols or the hash table of symbols, you try to find your symbol within this hash table, and if you can find it, then you return it, and if you cannot, you continue, but this time you move to the parent scope by doing scope is equal to scope the pref, which gives you the parent scope. And finally, if you couldn't find it in any scope, then you need to emit an error message saying, hey, this identifier was never declared anywhere, this is a mistake. Now, there's also a couple of other functions that find the enclosing loop. This is useful for break and return and continue, or not return, but break and continue, where you look at the AST node of the current scope, and if it's a while loop, then you return it. If not, you go to the parent and you look if it's a while loop and continue. You also accept, of course, for loops because both for and while accept the notion of break and continue. And if you find one of those two things, then you know this is the loop that is enclosing the state, the expression break or return, and then you can return that loop. And if you cannot find any loop for break or continue, then you emit an error message. In a very similar way, we have something that does essentially the same thing but for return, but this time we look for functions instead of looking for loops. Then we have functions that push and pop scopes, that basically places a new element on top of the current scope. What's interesting here is that we reuse the storage. So we allocate the storage of a scope once, and then when we pop the scope, we don't really release the memory of that scope. We just move the pointer of the current scope to the parent of the current scope, essentially. So we just move the pointer of the current scope. And whenever we need to push the scope again, that allows us to reuse the memory that we allocated the previous time, and then you just have to clear the hash table, but we can otherwise just reuse all the memory. So this is how it works. There's of course special cases when this is the first time you call the function, when there's over an existing allocated node, and when there's no allocated node, which you need to then create by essentially saying, hey, I'm creating a new scope, and this is the parent of that scope, and this function here is going to link the two scopes, the newly created one and the one you're giving as a parameter, and it's going to return the newly created one. And then, of course, popping a scope, like I said, you just move the pointer, you don't do anything else, do not release any memory. Memory is released when we destroy the environment, but when we move scopes, we don't destroy any memory. And then we have a helper function to bind many elements together, which is just, again, going over all the elements of an AST list and binding each and every one of them with a given function. Then we have what I talked about earlier, a function to insert declarations in the environment. What this thing does is just finding the name of the declaration and inserting it into the environment. And if it's not a declaration, obviously it just skips it. So it's useful because this is necessary if we want to have the behavior that I described earlier, where you have functions that can be used in any order. If I want to do that, I first need to put the functions in the environment and then go inside the functions themselves. So if you go to the program, for instance, the program which is here, what we do is at the top level, we push the scope, right? We create an empty top level scope, and then we're going to insert all the declarations that we see in the environment before binding them. And then we pop the scope. And that makes sure that every name is available at the moment we go through the actual contents of the declarations. And you can notice that we do the same thing for block expressions. So we go over all the statements, we insert the declarations in the environment, and then we actually go over the statements themselves and then bind those. Right, so this is important because it allows us to have some kind of name binding that is not dependent on the order in which we traverse things. Then there's also an important distinction to make. We have a function to bind expressions. And binding expressions is, like I said, to go over the expression, look at where identifiers appear, and when you see an identifier, then you need to connect this identifier to the place where it is declared. The way you do this is if you have a path, okay, if you have a path, then you bind it, which means you essentially set the declaration site that I just changed. So what you call target with decal site. You set decal site to the result of looking up the symbol made of the name here. And recall that a path could be made of many things. It could be A.B.C. And if you see this, then you can obviously find out what A is, because A should be available. But B and C are fields or members of A. And then you don't know what A is because you don't have the type of A. You don't know anything other than just the name of A, and that's not enough to figure out what it is. And so you cannot really connect B to anything or C to anything. So this is only going to look at the first element of a path and connect it. And what's important to notice is that there's a difference between expressions and patterns. You recall that when I talked about the grammar, I said that expressions produce a value and patterns capture a value. And what this really means is that the pattern is essentially just a declaration of an identifier, and the expression is use of an identifier, which means that whenever you see a pattern, the pattern is in fact a declaration. If you see just an identifier alone, if you see just a pattern made of fun f I is equal to I, of course this wouldn't type because I doesn't have a type, but anyway, I here is a declaration. It is a pattern, and it is a declaration for the identifier I. Whereas if I were to do a match expression, for instance, match some enumeration option, maybe I have an enumeration like enum E, which has two possibilities. There's A and B, maybe something like that. And I say match E dot A with E dot A, right? If you have E dot A, otherwise, I don't know, return 3, return 2, something like that. That's just an example. So here you notice I also have a path. However, in this case, I consider E.A to not be a declaration. It's a pattern, that's correct, there is a pattern, but I'm not declaring anything here. This is a path, it has more than one element, and therefore it is not a declaration, but rather it is a use. So there's a special case where you may have uses in a pattern, but it's only when you're using a type. And that can only happen if you have either a type argument after something, like I32 for instance. If I was seeing, for instance, something like this, I would know this is a type. Or if I had something like E.A, like a path with more than one element. So if either one of these two cases is true, then I know it's actually a real path and I bind it like a path. Now, for anything else, it's just essentially going over the elements of your AST node, the children of your AST node, and binding them. You don't bind them in necessarily the same way. So for instance, when you have a type pattern, which is just a pattern followed by a column followed by a type, then you first bind the pattern itself and then you bind the type. And binding a pattern creates identifiers, which is why it's different than binding the type, which just looks at identifiers and connects them to their declaration sites. So that's basically it. And then I think I've described essentially all of the name binder. Everything else is pretty obvious. It's just this notion of uses versus declarations, which I think I've covered. The fact that we can connect a break and continue to the loop by using this find and closing loop thing, or the return to the place where the function is having a return statement. So we can actually do this with this find and closing function I described earlier, and we have also all the expressions covered here. Right, so this is very simple. It's 400 lines of code, rather simple, and it does what we want. I've also changed a little bit the compiler right now to emit error messages. in a nice way, so you can actually see a diagnostic where the error happens. And that's really useful, and I'm going to just show this a little bit so that you can understand a bit how the compiler works right now. So let's go in this directory, this build directory, run the compiler on the file that I'm going to create. So let's create the file, bind.foo. I've already created it actually. This is an example where I'm going to display, first of all, the normal case, the case where f is available. Okay, this should be legal foo code, and we're going to see what happens. I'm going to run it, bind foo, nothing happens. I can print the AST, I end up with something pretty normal. That's okay. Now let's say I actually want to change the order. First of all, we're going to see what happens if I mistype something. Here I use H instead of F. That's a mistake. So an error should be reported because H does not exist. And as you can see, this is what happens. It tells me a known identifier H, which says, well, H does not exist, please fix this. So if I go back there, I just say this is F. We saw that this was accepted. What happens now if I place it before? It just works. So it just works because, like I said, the name binding algorithm first goes over the declarations G and F, puts them into the environment, then goes a second time over the thing, and this time connects the body of G to, well, basically using the environment that was just created, and figure out, okay, F was already declared there, so I know that this F here is in fact this F here. So that's what name binding does. One thing that is not necessarily super nice is that, let's say I have a function, I'm going to call that fun frob. Right, that's a valid function. That's fun frob. Now let's say I mistype it. I have another function G, and it's called frob, because I mistyped frob. Of course, it's going to tell me a known identifier fob, and it will be correct. But perhaps it should suggest that I use frob instead of fob, right? Because it's close enough. There's this question of how do I make suggestions about what identifier should I have typed instead of fob? And one of the ways we can do this is with Levenshtein-distance. So what we're going to do is we're going to add a Levenshtein-distance algorithm to suggest similar names when reporting an error. So as a reminder, Levenshtein-distance is actually very simple. It's a distance between strings, and the way it works is you're looking at a string as a list with a head and a tail. So you have two lists. There's like, let's say fob and frob, okay? And so at this point, what we want to do is say, okay, what is the distance between these two things? So Levenshtein-distance says, well, what we do is we look at the first character. And then there's the question of, is the first character the same? If the first character is the same, we return essentially, we know that this part of the string is identical, so we can just cut it out and then recursively invoke the distance with whatever remains after removing this first character. So we have OB here, and here we have row B. And here, as you can see, this is no longer the case. There's a character that differs between those two things. And so what Levenshtein-distance does here is we can essentially look at three different cases. The first case is the distance between OB and rob, where we remove the R, that was the problem. That would give me a distance of 0. So let's just indent this to show that there's different possibilities. Then there's another case where actually, the problem comes from the left-hand side, so I'm moving the first character and computing the distance between B and OB. And to compute the distance between B and OB, what I do is, again, I recursively invoke the Levenshtein-distance, and in this case, it would say, well, the distance here would be, well, a distance of, again, either the first thing would make a choice. I would have to either remove one character from here or one character from there. And if I decide to remove one character from here, I would say, well, this is the empty string, and here I have OB, and the distance is therefore 2, because the empty string with distance compared with another string would be a distance of 2, because there's obviously 2 characters more in one string than the other. But then the other option would have been to keep B but to remove the O from the other, right? So there would have been B and B, there would have been 0, right? Which is nice. And there's the option of also saying that the first character is just different, the rest is the same, right? Which in this case would be first character is different, well, we remove it, and the rest is the same, and that would be a distance of 1. And what you do then, once you have computed all the 3 options, which is, first of all, like I said, as a reminder, we first remove the head in the left-hand side, then we keep the right-hand side the same, and we compute the distance. Or we keep the left-hand side exactly the same, but we remove the head on the right-hand side, essentially the reverse, we get distance of 0 here. Or we essentially say that the first character is different, and that's life, we just remove it and look at what remains after that. And this is 1. And so what we do here is, in all these cases, there's essentially one change that we made to get there. So we essentially consider that this is 1 plus, and then we see that, okay, we have 3 options. So if there's a mistake, the mistake is most likely the one with a lower cost, which is the one here with distance 0. So it will be 1 plus 0. That will be the real distance between those two strings. So that will be essentially a distance of 1. And then we do the same thing I mentioned earlier, which is to consider that the first character is anyway different, and there's nothing we can do about this, but remove it from both options. We get B and OB. What did I do there? Well, that was already what I did there, actually. B and OB. So the first one was OB and OB, so I essentially removed the R. Here I essentially remove the O, and here I remove the R, so it's the number 3. So the case number 2 is actually I remove the O, but keep the R. And then I recursively invoke the algorithm to figure out the distance between these things. But I know that by definition the best case is the 0 here, right? Because the minimum cannot be lower than 0 here, right? So instead of computing B and row B, I just forget about that and say, okay, it's 1 plus 0, and the distance between this is 1. I don't want to bother computing this. And then here I can go on and say, well, the distance with this is essentially 1. So Levenshtein distance between these two things is essentially a count of the mistakes that you make, right? If you make a mistake, you can either replace something, but then if you replace it, you change it with another character. So that's essentially the same length, right? So it would be like I'm replacing something like, let's say I have ABC, and I replace one character, so I have BBC, for instance. I replace the A with a B, that's one possible mistake. But I could also say, well, instead of replacing the A by a B, I can also forget the A. That's another type of mistake. There's also another type of mistake where I insert a character for some reason. So there would be ABC, but I'm inserting a B in front of it. And so Levenshtein distance is essentially a way to compute the distance between those two strings. And then we can use the distance between the string that we're seeing here in the source file, the identifier that the programmer types, and the identifiers that we have in our list of symbols. And then if we see a good match with a distance that's small enough, then it means that that's a potential suggestion, right? So we're going to implement this Levenshtein distance, and then we're going to implement the function to suggest things. Let's look at, first of all, a function to implement the Levenshtein distance in the most stupidest way possible. So let's write it here. So static size t, let's write it int Levenshtein distance, and we do const char left, const char right, and then we're going to essentially compare those two things. So first case is if left 0 is equal to right of 0. So something like this, sorry. They're identical. So what we do is, because they're identical, we just return the Levenshtein distance of left plus 1 and right plus 1. And if we do if left, we have to handle the case where this is the empty string, obviously. So if left 0 is equal to 0, or let's just say something like what people would actually write, something like if not left, we are actually 0, so we would have to return the length of the right string. And if we are on 0 on the right side, we have to return the length of the left string. Because that's how many characters differ. If we are an empty string on the left or an empty string on the right. Now, if the first character is the same, we just skip them and return the Levenshtein distance of the things where we skip the other character. Otherwise, then we have a mistake, right? We made a mistake somewhere. So what we do is we need to compute the three options I talked about. One of them is moving the distance, moving the character on the left, then the other is moving the character on the right, and the third one is moving both. So what we're going to do is compute all these things. So int a is equal to Levenshtein distance, and I can write b, c. These are the three options. One of them is to say, well, I'm computing left plus 1 and right. The other is left, right plus 1 and left plus 1, right plus 1. And then what I'm going to do is I'm going to return the 1 plus the min. And the min is the min of all three. So it's a is less than b, a, b, min is less than c, min c. Let's just write this like this. All right. So there we have it. We have the distance that we're talking about. It's definitely not the fastest version. We could also just skip things, in the example I did, which I actually removed. But if you look at this, I was able to skip this one because I knew that the distance here was 0 and there's no way the distance here could be smaller than 0. So we could actually implement something like that, a bit more clever, because we could actually have a minimum distance and know, well, the minimum of this has to be at least this, and because we know that there's 1 plus something every time we increment by 1, so we know actually a bound that is actually more precise than just 0. Anyway, so I'm just keeping this stupid for the moment, and we're going to write a small function to suggest an identifier to the user. So the way I'm going to do this is I'm going to create a new function called find similar symbol. I'm going to write here. And the idea is I'm going to suggest the identifier that might be useful here. So let's even call this suggest. And I can move this function a little bit up. All right. So here, well, we don't need the hash. What we can just do is start with the current scope and walk up the scopes. Then we're going to find instead of finding things in the hash table, we're going to iterate over the elements of the hash table. So I'm going to do something like force st I is equal to 0, I is less than scope, arrow symbols, dot capacity, I think is what I have to be looking at here. And then I'm going to look at the minimum distance. So to find the minimum distance, I'm going to do int min distance, and I'm going to say to 3, because 3 arrows is reasonable. More than 3 might actually be too much. So what I'm going to do is change the error message first to not mention a location, because if I mention a location, a diagnostic is going to be emitted. Then say, did you mean with question mark? And like can also store the name. Alright, now the thing is that we have a hash table, which is a linear hash table, and some elements of the hash table are not occupied. So to test for this, there's a function called isBucketOccupied, which I'm going to use here. IsBucketOccupied, scope, symbols, if it's not occupied, I'll continue. Then, if it's occupied, then I need to know the distance. So if Levenshtein-distance, I can do int distance, or int dist is equal to Levenshtein-distance between the name and the symbol at this position, which is there is equal to symbols is equal to scope symbols elements. It can be symbols I dot name, and if dist is less than min dist is equal to dist, and similar name is equal to symbols I dot name. So what this does is just looking at all the symbols and trying to find something similar, and then if it cannot find one, then we don't print the message. But if you do find one, then you print that message. What I also want to do is to suggest similar symbols only when the length of the identifier is greater than the minimum distance, because it wouldn't be good otherwise, right? Because if I have just say something like int I, then if I just make one mistake and say, well, j instead of I, is going to suggest me to use anything that is just one character, like x or k or t or any of those things, which is not really helpful actually. So it only really makes sense if the name, or the length of the name rather, is longer than the minimum distance, right? Otherwise I'm just saying, well, make as many mistakes as the name is long, so that doesn't really make a lot of sense. So if strlen of the name is greater than min_dist, or is lower or equal to min_dist, we just return do not suggest similar symbols for identifiers that are too short. And of course it's going to say to me that one is size t and the other isn't. So what I'm going to do is, well, change this to size t, I guess, because it's always positive, never will be negative. No point in storing this in something like that. Alright. Then I just have to call this function after reporting an error in the identifier. If, or I just suggest with an environment in the name. I don't think I need the location actually. And then because this is called here, I need to move the code above. Alright. Now this should work. And it says unknown identifier fob, and as you can see there's no similar symbol, and I suspect this is because the name is not long enough. Maybe I say minimum distance is true. And now it works. Did you mean fob? Unknown identifier fob. But this is not really a good example, because maybe if I just have another identifier like God, this is a better choice, right? And it still chooses fob. And that's not really a good sign, because the distance between well, the distance is the same actually. frob is just one mistake, so it's perfectly normal. So in frob you have the mistake that you added one character, the R. So this is the mistake of doing this essentially, and then removing that. And in fob there's another mistake, but it's just one as well, which is to do this instead of that. So they're essentially the same distance. So this is why one is arbitrary choosing the other. But if I were to do gab, then I guess, well, it will still choose from, yes. But now let's say I do frab and I do gob instead. It should select gob exactly. So there you see gob. So this is what we wanted to see. This works, and I think I'm going to leave it at that. This gives you an idea of, first of all, how name binding works, but also what you can do to improve user experience in your compiler. So this is this type of interesting additions to your compiler that make your compiler a slight bit more friendly to the user, and I think that makes a world of difference, particularly if you have good diagnostics like those here, which show the error line and a good suggestion right below it. Here it's not perfect because I think I need to move this note here a little bit above to be shown right after the error to say, well, the note is actually connected to this error message. But other than that, I think it's pretty clear that this is pretty helpful. All right, so I think I'm going to leave it at that. Go back to the introduction slide and then say that the next time we're going to look at type checking, and I hope to have implemented a big or large part of type checking by the time we look at that. And type checking is of course going to be implemented according to a bidirectional type inference algorithm, which essentially means that we're going to infer types with a type system that is reflecting the algorithm in its rules. So we're going to write essentially typing rules, and those typing rules are going to give us an algorithm to infer types in the program. All right, so I hope that was interesting, and see you next time. Thank you for your attention.